Hi everyone, this is the question and answer video for the Chapter 19 discussion board. Okay, our first question was asked by Quaid. On a molecular level, what makes a substance more or less combustible? Is it structure or electronegativity or a combination of the two? The answer to this question is that it depends on the thermodynamics and the kinetics, especially. So if a substance is going to be combustible, then the reaction with oxygen must be spontaneous, because that's a combustion reaction. So if we have some substance A, and then it's reacting with O2, then a combustion reaction, if you recall, is going to result in H2O and CO2 at least. I don't know, maybe some other stuff too, and there's going to be some stoichiometric coefficients to each of these. And so the delta G of this reaction is going to need to be spontaneous, so it's going to need to be less than 0, and probably far less than 0. In addition to that, a combustion reaction is very likely to release a lot of heat, so the enthalpy change must also be much below 0. And so if you're thinking of combustible in the sense of being explosive or producing a lot of energy in a short amount of time, then that means the rate constant of the reaction is going to need to be large. So if we have a rate constant K, then the K is going to need to be much greater than 0. So that's going to make for a fast reaction. So then how does this depend on microscopic properties? Well, it just means that the bonds in the reactants are going to need to be fairly weak, so high energy. That's going to be one factor. And what makes for a fast rate constant? Well, that just means a relatively low barrier between the products and reactants. So if we have reactants on this side and products on this side, then this activation energy barrier to the transition state is going to need to be fairly low. That's what makes for a fast rate constant. Okay, the next question I got, and I got quite a few of these, was to see more examples of detailed balance to help you understand what that is and how we use it. So I'll give a couple of examples here, since this seemed to be a pretty prominent question. I'm going to give you a real life example that I published a paper about. So what I told you in the lecture was that if you have K on and then you divide K off, this equals 1 over KD, where KD, remember, is the dissociation constant. And the reaction we're considering here is some enzyme with an inhibitor forming a bound complex. And the rate constant in this direction is K on, the rate constant in this direction is K off. Now I ran some computational calculations, and I found a K on of 2.1 times 10 to the 7th per molar per second. And I found a K off of 83 per second. And this was for a trypsin benzamidine system. Trypsin was my enzyme. It is a protein that is often used for assays of this sort. And benzamidine is a well-known inhibitor of trypsin. Okay, so I calculated these two quantities, and this is the formula that I pointed out to you for detailed balance of inhibitor binding. And so once I performed this calculation, I was immediately able to get KD. And the value I got for that was 3.95 times 10 to the negative 6 molar. And when I go to plug it into the equation for the delta G of binding, I actually have to enter in the gas constant R, the temperature T, and then log KD. But then I actually have to divide this by 1 molar so that I can get rid of that unit and perform the logarithm. And I calculated a delta G of binding of negative 7.4 kcals per mole. And so this was my calculated value. And to compare this, the experimental value that was measured in the lab is negative 6.7 kcals per mole. So as you can see, I got a value that was very close. So this is a real-life example of detailed balance. We are relating kinetic quantities to thermodynamic quantities. I'd like to give you one more example of detailed balance, because so far we've only seen detailed balance for two different states, products and reactants. But what if there are more states available to the system? What do I mean by that? Let's use the example of protein folding, because this is a subject that's very interesting to me, and it seems like it's a fairly interesting subject to many of you. So we've got an unfolded protein here, and it's possible for that protein to fold a certain way, like that. And we can call this the rate constant from A to B, because we'll call the unfolded state A, we'll call the folded state B in this way. But maybe it's also possible for the protein to fold in a different way, like that, maybe. And we can call that state C. So there's going to be a rate K A to C. But of course, it's possible for each of these states to unfold. So that's going to be KB to A, and this is going to be KC to A. And then maybe it's also possible for the folded states to just immediately transition between each other. So there's going to be a KB to C and a KC to B. Now, what detailed balance tells us is that the rate from any of these states to any other state is going to be equal backwards and forwards. So the detailed balance assumption tells us that the rate from A to B is equal to the rate from B to A. And the rate from A to C is equal to the rate from C to A. And the rate from B to C is equal to the rate from C to B. All right? This is valid for a system at equilibrium. What can we do with this? Well, we can construct the rate laws for each of these elementary reaction steps. So for instance, let's take the rate from A to B. What's going to be the rate law? It's going to be K, A to B, times the concentration of A, because there's just one reactant. And the rate from B to A, well, that's just the rate constant, B to A, times the concentration of B, because B is the only reactant for that particular step. And since detailed balance tells us that those rates are equal, we can write down KAB times concentration of A is equal to KB to A concentration of B. And this is the sort of equation that we can make with detailed balance. So what does detailed balance tell us would not happen? If we make the assumption of detailed balance, we cannot say that some sort of cycle would form. So this would not happen under detailed balance, where you have unequal rates flowing in sort of a cyclical direction like that, where A goes to B and then goes to C, which then goes back to A. Detailed balance would not let that sort of thing happen, where you get sort of a cycle forming. However, in real life, systems can exist outside of equilibrium if energy is being expended and entropy is being expended to hold it out of equilibrium. And so occasionally in our cells and in our bodies, we do get cyclical processes, and in that case, detailed balance is being violated. But most of the time, detailed balance holds true. And unless you have a good reason to assume otherwise, we can assume detailed balance for chemical and biochemical systems. Okay, the last question came from Allison Hale, and she asked, I'm slightly confused about differential rate equations. For example, in problem 7b, chapter 1819, Mastering Chem, why is K2 being subtracted from K1 instead of added? All right, so I realize in hindsight that I probably could have spent a little more time on this. But here we go. Here's how you construct rate equations and rate laws. You need to know the elementary reaction steps. Because if all you know is the overall reaction, then you're not able to do this. So for instance, if we have an elementary reaction, A goes to B, and then B reacts with C to go to D, how can we make the differential rate equations for each of these steps? Here's what we do. First, we have to identify the rate constants for each of these steps. And actually, let's say that there's a backwards step. So there'd be K minus 1. All right. If we want to form a expression for the rate of, I'm actually going to do D first before we do any of the other ones. The formation of D, if you know the elementary reaction steps, then we can look at the particular reaction in which D is involved, and we have to look at all of them. So once we get to B, I'll show you what I mean. But D only exists in one step. So first we ask, okay, is D being formed or unformed by this step? If it's being formed, which it is, then it's positive. And we have to look at the rate constant, K2, for that step. And then we look at the tail of the arrow, and we see which species are present. And we put the concentrations of those inside there. Now, if there had been like a 2 out here like that, then we'd have to put an order of 2 above that concentration. Okay? But if since it's not there, then we can just go ahead and leave it like that. And that's it for D. What about a trickier one, like B? Actually, let's do A first. So first, A can be either formed or unformed using this particular reaction. It can be unformed by the forward step. And since it's being unformed by the step involving K1, we'll do minus K1. And then look at the tail of that arrow. A is there, so we put that in. But A can also be formed by the backwards part of this reaction. So it gets a plus, and then a K minus 1, because that's the rate constant for the backwards step. We look at the tail of that arrow. That's B. And there we go. That's the rate equation for A. Let's do the trickiest one of all. This appears in both steps. So we're going to have multiple expressions here. First of all, it is formed by the forward reaction of this step. So it's going to be K1, look at the tail of that arrow, A. And it's positive because it's being formed. B is also being unformed by the backwards step of this reaction. So it gets a minus, K minus 1, and then B is at the tail of the arrow, so that's what it gets right there. It additionally exists in this reaction here, and it's being unformed in this step, so it gets a minus. The rate constant is K2, and at the tail of the arrow, it's both B and C. So there you go. There's an example for how you would construct the differential rate equations for a problem like this. And if you want to ask about this problem specifically, feel free to reach out to me on a one-on-one, problem 7b, then feel free to reach out to me on a one-on-one basis by email.